Okay, welcome back everybody. We're now in a virtual mode of conduct. And so we'll be doing everything virtually for the next week and a half or so. I'll have videos for everybody to watch, static videos, and we'll be doing live interaction with you in this moment. It is difficult to do an interaction over Zoom. So we'll have the chat window going, so if you have a question, chime in there. So I'm just going to be pretending to give a lecture. Sierra will monitor the chat window and she'll just give me a very subtle nod to say that I need to read something. So she's not going to jump out of the box and be like, Jingdon's got a question right now. So we did this last year. So during the spring, and we had a lot of those, which scare me. So anyway, we're going to try to make all this stuff work. We still have Slack, we still have all the other modes of communication. Campus is not closed, so it's just that we're not hosting in-person classes. So if you guys need to meet with somebody or anything like that, I can meet you out on the drill field or something like that, and we'll make everything work. Everything will be due at the time of the final exam. I guess I should look at this camera, right? At the time of the final exam, everything will be due. And so you'll submit everything to Sierra. So we'll have her collect everything and then we'll go through everything. There was a mixture problem that we played around with on the last homework. So you ended up sampling from a mixture model, 4 different normal distributions. And that's a classic problem, that there's 4 different distributions in which the data comes from. And what we did with that problem is we misassumed that the data came from only a 1-component model, a normal distribution. And you got to play around with how p-values behave in hypothesis testing situations when you got the wrong model, and we saw how Bayesian methods ended up performing. I had asked you to just think about what would be the correct thing to do. And the correct thing to do is to infer the true mixture model. Try to figure out how many components are there and figure out what their underlying parameters are. If I gave you the data and I labeled it and I said this data came from component 1, other data came from a different component, if they were all labeled, you just fit those different models independently of each other. But what we get in a lot of real situations is a whole bunch of data that comes into us and we don't know how many components there are, and we don't know the labels on all of the data. We don't know which component derived the data. The correct thing to do is, in my opinion, to just estimate what the true model is. And so there's a lecture that we provided for you. Sierra gave that lecture last year. And so if you want to read up on mixture models and the correct thing, you can do that. If you end up writing down the algorithm for fitting the correct mixture model in a Gibbs sampling fashion, I'll give you some extra credit. So we're not going to cover it here, but I think all those resources are there. So how much extra credit? 10% midterm. So what do I want you to do? Tell me how you do it. So you might say, well, I don't know what you expect. I want you to tell me how to do it. So it would be a 1 or 2 page write-up if you want the 10%. It's on Wikipedia. Sierra gave you a lecture on it. That's been posted. I think we ended up posting specifically the date that she gave that lecture. That's in last time's lecture. So just watch the YouTube video and it has all the instructions for you. So we'll post another announcement on Slack a little bit later. Maybe Sierra will give you a pointer to the video where it describes how to do this. She even gives you the code in that video. So I've seen it. So it happened. It's hard to remember what we've done before. Okay, so that's just a simple announcement. More extra credit on the books. We've also got the Behrens-Fisher problem that's extra credit. And Sierra gave a lecture on that as well, and we pointed in that direction. So Sierra, if you don't mind taking a note, pointing in the direction of your mixture model lecture on Slack. So another opportunity, if it's too overwhelming and you have too much to learn right now, forget about it. You don't need to do this. I'm going to carry on and I'm going to go into model selection. So lots of stuff to learn. Just real quickly turn this off. How do you? Black. Okay, there we go. Okay, so technical difficulties, we'll get past them. So I want you to consider this model. So y is equal to x beta. So we've been playing around with this a lot. And so I put model in quotations simply because it's not like a real model. It's not a physical model. And so what we're doing is we're trying to figure out what is the linear relationship between these x's and these y's. And that relationship is going to be determined by their influence. And those are coming from the betas, and that's what you're to estimate. And so you estimate these betas usually. See which ones fit the best. And there's a lot of ways to do this. So I want to just point out in my notation the betas are p-dimensional. So we ended up having for each associated y a vector of x's. And the influence of these x's on y are determined by these betas. And so the name of the game is to fit the betas. Now we've done this many, many times. So one solution for the betas, so one possible solution, and a lot of people use this solution. So this is probably the most popular solution. So beta hat, so that's my estimated quantity of betas. I'm assuming maybe there's some true betas, and we need to estimate them. And so that's just x transpose x inverse x transpose y. And some people call these the normal equations. You should have this completely committed to memory. Now I want to point out that we do need to invert a matrix right here, and sometimes it's not possible to do. So for instance, if p were bigger than n, so how many data points I have, this matrix will not be invertible. You won't be able to fit it. This is not full rank, and so this solution does not exist. And so you might not always want to work with this solution. So if you've got a relatively small number of betas, you understand the system you're trying to estimate, you've got a lot of y's, and the relationship is linear between the x's and the y's, this is a pretty good solution. But of course, if p is greater than n, if I have columns that are collinear, so they're multiplications of each other, this will not be invertible. So it doesn't always work. So I'll just make a note. Note, this doesn't always work. Okay. And I assume that you guys have had some form of regression in your life, so I think I won't say too much more about this. But we need to come up with solutions in general. So if p is greater than n, it might be the case that some of these data points, so maybe the second one right here in this column, associated with beta 2, maybe those don't really explain y very well. Maybe there's no relationship there. And if that were the case, then we would want to drop this column out of the matrix if it didn't have any association with y. But we don't know in advance which columns to drop out of the matrix. So what we're really going to do is we're going to try to estimate whether or not this coefficient is a 0. So maybe it's equal to 0. And that would be the same sort of solution. So dropping this column out of the matrix right here would be equivalent to setting beta 2 equal to a 0 in the model. Yeah, so I didn't put the error term on. So I got a good question that somebody said, why no error term? So I haven't really talked about probability or statistics yet. And so I'll mention something about that in just a moment. So that was intentional. So usually there's Gaussian error sprinkled in right here. I haven't said anything about that, and that is intentional. So I'll lead up to that in a moment. This solution can exist for different people regardless if I write down what the error assumption is. And I'll make some points about that in a moment. But good catch, good call, but intentional. So I think the name of the game is to figure out which of these betas is actually equal to 0. Now, for a Bayesian or a statistician, we would include an error term. So plus error. And that error might have some assumptions, and maybe it's normally distributed error. And if it's normally distributed error, I've told you what a Bayesian will do. So they'll encode a Gibbs sampler. And so this is just a Gibbs sampler. I'm just iterating through some large number of times. So this is like 1,000,000. It's a big number. So you want to run this thing a whole bunch of times. And what you're going to do is you're just going to iteratively sample from the full conditional distributions. And so this distribution right here we've talked about in some detail, and I'm just conditioning on everything else. So just to be specific, the conditioning is on X, it's on Y, and it's on all of the other betas. So I would say I'm going to call this beta minus P at the last iteration, T minus 1. And so this right here, beta minus P, is just this vector. It's going to be beta 1, T minus 1, all the way up to beta P minus 1, T minus 1. We're going to skip over P, so I'm removing it from the set because that's what I'm sampling. So this will be beta P plus 1, sampled from the last iteration, so on and so forth. I'll say all the way to beta cap P, the dimensionality. Now, I've kind of messed up here. This is not quite right, because when I sample the Pth1, I actually have more updated versions. All of these right here, they've already been updated in the loop. And so all the way to here, these have already been updated. And so what we want to do is we want to use our most current information. And these ones still need to be updated. And so what you're going to do is you're going to sample this from its full conditional distribution. Under the point mass prior, this is going to be a point mass distribution as well. So what does this distribution look like? It's going to be some posterior distribution, and it's going to have some spike at 0. And so this is that mixture that we've been talking about. In the last lecture, I told you how to sample from that distribution. So what you're going to do is you're going to come up with the probability, the mixture weights between these two things. You're going to flip a coin with that probability. If the coin lands heads, this thing is going to be a 0. If it lands tails, then you're going to sample from the posterior distribution for that beta. And I wrote down the Bayes factor for this, and I wrote down what that probability is. So this probability that you're going to be flipping, basically what you're sampling from is the posterior probability that beta P, right here, at the Tth iteration is equal to 0, given everything else. So everything else is all that other stuff. So this probability right here is 1 plus the Bayes factor for beta P equal to 0. Invert, invert. Oh, and there's some probability masses in here as well. Pi naught, 1 minus pi naught. This gets inverted. Invert. So I've shown you what that Bayes factor is. I've derived it for you. You can go and show the details of what that is, but it's a calculus problem that you've done many times now. So this is that algorithm. Basically, you're just iterating over the full conditional. So in some iterations, the betas will be zeros or they'll be non-zeros. And if there's a high proportion of zeros, let's just say for this P1 right here, so I'll just say this is a specific P. The frequency of the times you sample is 0. It's the probability that it's not in the model. So let's say 90% of the time, updating this specific beta is 0, then I probably don't think that that beta is very informative about the data. And this is called the stochastic search variable selection algorithm. Search variable selection. And there's a lot of implementations of this algorithm, but this is probably the easiest one to play around with. Now, what I had done for everything in the Bayes factor that I worked out, I actually integrated all of these other betas out of the equation. So you can update using the current betas, and those are going to be changing every time you update. I'll say something about pi 0 in just 1 second. I forgot where I was at. So, integrating out the betas. So, I've shown you the Bayes factor where these have been integrated out already. So, I've removed those from your equation, so what you're going to be conditioning on is just the x's and y's. You can look at the details. Somebody just asked, what are the pi naughts in here? So these are your priors. So this is my prior on if beta p is equal to 0. And so the question is how do you pick it? I don't know, what's the problem? So it depends on the context of the problem. Saying that, it's not a very sensitive parameter in the model. And so I would usually pick these to be maybe 1/2. So what's the probability that beta p is a 0? Maybe it's a half. So maybe it's something other than a 0. I don't know. It depends on how much you want to press these things towards 0, but it's not highly influential. So I think most people just plug in a half, and in that case, this whole thing would just cancel out. So that would be my recommendation for you. When you're doing the homework, use a half there. Okay. This is a pretty sophisticated algorithm, and sometimes it takes a little while to get your head around everything. There's ample notes, papers. I would say papers have been written on this in different ways to play around with what you're sampling from right here. There's thousands of papers on this. But if you want to search Google Scholar or something like that, you'd be looking for SSVS. And I would append Bayesian to it. If you write in Bayesian SSVS, you might even find code on the web so that implements this for you. There's a lot of packages for doing this. In R, there's a ton of packages. I would like you to try to implement your own. But if you get too stuck, feel free to use the resources at your disposal. That's how we operate these days. There's other solutions to this problem. So I ended up saying in model selection, there are a lot of techniques. And so basically what we're doing is we're hypothesizing and doing hypothesis testing on whether or not these things are zeros, and we're just running through it sequentially. And so we're adapting all of our hypothesis testing methodology to selecting models. So I usually say I don't like hypothesis testing. And I really mean that in the context of you've got a couple parameters. You know, mu is equal to 0 maybe in a normal model. I don't think that that's very appropriate to even ask such a question. It's like just estimate what you think the parameter is. And if it heavily overlaps 0, then maybe it's close enough to being a 0 to remove from the model. Or to set equal to 0. But I'm kind of thinking about this as being very high dimensional. So however many betas I have. And so you really have to do something. So you can't just sit there and like, let's estimate everything and then see which ones we think are zero. That would be a tremendous task. So I think all of this stuff can be adapted to model selection, but all of the controversy in hypothesis testing lends itself to controversies in model selection. So if you've been going to stat conferences for a while, you've seen ample presentations on this. Every statistician somewhere has a paper on model selection, how they do it. And really what we're arguing about is how much are we trying to enforce these things to be zero? So how much pressure are we giving it? So in this algorithm, I get pressure to push these things towards zero through the pi knots, but also in the point mass prior that we used, that diffusion part. So I was calling it psi. So what is the alternative prior? And that has a lot of influence on things. And so a lot of people have been playing around in adapting that function. You know, what your prior on the alternative hypothesis is. Okay. I'm going to leave this for you guys to play around with, work on. You have a homework assignment. I've given you 3 different data sets on the web. And so I want you to figure out which models I use to generate those data sets. And this is kind of how the real world is. Somebody gives you data, or you get data and you don't get to know what the true mechanism for generating that data is. And so let's see how close you can come to the models that I actually used. Obviously it depends on n, what p is, and what I've done to the data. I didn't include any interactions, so I'll just give you a heads up, no interactions in my model. So fairly small set of models you have to look through. So I think in some of them I gave you like 10 covariates. How many models are there? 10, 2 to the 10. You might also want to think about your intercepts and add one more parameter to everything. If you don't know what I just said, look up why it's important to maybe look for intercepts. And so I may have included an intercept in the model, and that's not already encoded in the data that I handed you. Okay, enough rambling about that. I want to tell you about a couple different competitors to the SSVS algorithm. So this is a heavily computational thing. You need a lot of computer power to do this. So that kind of prohibited doing something like that in the 80s. But I'll show you a solution that they could have done in the 80s, and in fact they did it in the 1800s. So in the 1800s, people had already considered this problem. So let's say I've got y is equal to x beta, so same model. And so one possible solution to find those betas is looking at x transpose x inverse x transpose y. Of course, if the inverse doesn't exist for x transpose x, the solution doesn't exist. And so I think people back in the 1800s were very well aware of this, and they wanted to do something. So here's a possibility. So instead of just maybe looking at a problem like this, you might say, instead of looking at y is equal to x beta, you might look at the difference between these two things. And you might try to place some sort of a norm on it all. And so what this is, right here, just to give you some notation, this is the 2 norm. And this looks just like this. So y minus x beta transpose. So this is just a vector right here. This will be a row vector. And then I'm going to multiply it into y minus x beta itself. And so there's another way that you could write this. I'll just say this is equal to the sum of the yi's sum of the yi's, there's n of these, minus xi transpose beta, so the associated x with y. And then I just square that thing out. So these are just sums of squared errors. Some people like to try to solve this problem. So if you weren't a statistician, you might think, I can still come up with some good solution to try to minimize the difference between the yi's and the xi betas. So some people like to look at this problem and look for the arg minimizer over beta of this function that we just played around with. Y minus x beta 2 norm. You might be asking, what am I doing with that right there? It's just notation saying that I've squared everything out. Technically, the 2 norm itself has a square root over the top. If you didn't know that, it wouldn't change the solution to this problem because that's a monotonic function. Okay, so some people might call this beta hat. Now, sometimes this solution exists, and when it does exist, the solution, oops, I think I just lost the board. So beta hat, the solution to this is x transpose x inverse x transpose y. And this is just a calculus problem. So all I have to do is basically take derivatives over the betas, set them all equal to 0, and solve for the betas. What do I get? I get this same solution that we've talked about many times in class. Of course, this solution requires the inverse to exist. If p is greater than n, this solution does not exist. So this is the solution that they came up with back in the 1800s. And I believe this is attributed to Tiganov. And I'm not going to try to spell that. But if you weren't in a statistics class, they might be talking about regularization techniques. And this is called Tiganov regularization, or as statisticians call it, ridge regression. Okay, so I still haven't introduced the error term here. And we don't need the error term to come up with an optimal solution to some problem. So I personally, as a statistician, I like the error terms because I like to assume, what the distribution over the residuals looks like. So ridge regression is this problem. So it's a slight deviation from this problem right here. It looks like this. Beta hat ridge is equal to the minimizer over beta, or the argument that minimizes everything. And this is going to be same sort of formulation. I'm going to look at the difference between the x betas and the y's. But I'm going to add a little bit to this. And there's different ways to formulate this problem. This is equivalent to a constrained optimization. So there's a lot of ways to kind of phrase this problem. The way I'm writing it down is the solution to a Lagrange multiplier problem, but we don't need to talk about those details. They're not all that important. And so this thing right here is going to be greater than 0. So greater than 0, this thing's positive. And so what we've done with this is we're looking at the same problem, but we're adding a little bit of a penalty. Now, just to be super clear about what this is right here, this I could write down as beta transpose beta, or I could write it down like this. This is going to be p goes from 1 to cap p, beta p squared. Those are just the squares of everything. And so I've got this extra penalty right here. This is positive, that's positive right there. And so what this extra term, and I'll give you a name for this. This is called a regularization term. So this is regularizing. That's not going to work. It turns out if you pick this thing to be positive, the solution to this problem always exists. And so it's just another calculus problem that you need to solve. And so I could differentiate everything with respect to the betas, set it equal to 0, solve for everything, and voila, I get a solution. And so this solution, I can just write it down for you. It looks like this. X transpose X. Not inverse yet. There's something else that's going to go in here. Plus, or times X transpose Y. And so the extra little term right here is plus lambda times the identity. And so the identity is just diagonal of 1s and everything else 0s. Now I want you to convince yourself this thing is always invertible. This might not be invertible. It might not be full rank, but this is always full rank. And everything's positive right there on the lambda. So if that's going to be positive, this thing is going to be full rank. And you can invert it. The question is what is the lambda that we pick? So how do we pick this parameter? And what does it mean? So this is an influencer, I'll say. It influences how bad we want zeros in our model. I'll say how much we want to induce zeros. So how much force am I going to put on this stuff? So I don't want this solution per se. Even if it existed, I might not want that solution because maybe I just have too many betas around that are too close to 0. And so when you think about this function right here, this is penalizing how big the betas should be. And so, but I'm doing it in a squared sense. So I'm putting a penalty on beta squared, on all of these little things. So I'm forcing the betas towards 0. So I'm pushing them towards 0. So I don't want this thing to be too big. What we're trying to do is minimize over all of this. So since I want to minimize this, and I've got this penalty right here, it's saying I don't want the betas to be large. And so this is a computational thing. And how you figure out lambda is the whole name of the game. So you usually don't want this to be huge. If I made it 1,000,000 or something like that, I'd probably be forcing all of those betas towards 0. And then I would have nothing in my model that explains the y's. So if I made this 0 right here, then I would be back in this case, and I have no penalty whatsoever. And so it's really a question of how hard do I want to push those betas towards 0? So in an optimization sense. And that's really the whole thing in model selection altogether, is how much do you want to push the zeros, everything towards 0? Now in our point mass prior SSVS setup, we do that both through pi naught, our prior probability, but also we do it with that diffusion parameter in the alternative prior. So if I make that really large, I'm going to end up saying that I want everything to be zeros. Now Bayesian is doing it in a different way. This solution isn't all that great in the sense that unless you jack that thing to be really large, like infinity, you're not actually going to induce absolute zeros in the optimization. So you only get close to zeros with this formulation. Now, some people might like that and say, anything that's like below some threshold, I'm just going to throw out of my model. So this isn't truly doing model selection. It's kind of a push in the right direction, I would say. So saying that, the solution is very easy to get. And sometimes, if I've given a lot of data, I might use this as a cursory attempt to just rule out some of the betas. So I might do that. There's another formulation to this problem that is entirely Bayesian. So now I'm going to introduce the error term. So what I've done over here is I just considered an optimization problem, and that optimization problem has the same solution as the Bayesian would come up with if they were using a flat prior on the betas. So here's the Bayesian interpretation. And maybe some people call this Bayesian ridge. I think Bayesians just call it ridge though. And they say I did it in a Bayesian way. And what they mean is they're going to write down this same structural model, but they're going to add the errors. And the errors, in our case, are going to be normally distributed. So I'll just say these right here, error 1, all the way down to error n, where the errors themselves are normally distributed, centered at 0, and I've got some variance in all of this. And so what a Bayesian can do is they can write down their likelihood. So step 1 of any Bayesian model is to write down the likelihood function. And we've done that a lot of times. So I'm just going to write that down. This likelihood is going to be proportional to e to the minus 1/2 y minus x beta transpose y minus x beta. So that's the likelihood function. And I do need my sigma squared in here. You'll notice that this function right here, we've already seen. And so when we did the optimization, we were optimizing this 2 norm right here. So this thing right here looks just like y minus x beta in the 2 norm squared. And so the Bayesian is playing around with this same function that we just considered when we didn't introduce the error term. They're just saying distributionally, maybe the answer to this is the center of this thing right here. So if I went to optimize and maximize this function and look for the maximum likelihood estimator, I would get x transpose x inverse x transpose y as my solution. And so this is a monotonic function of this thing. The minus sign turns our minimization problem into a maximization problem. And so if you're minimizing this thing right here, it's equivalent to maximizing that. Now the Bayesian takes it one step further, and they add a prior. Let me get rid of that. And just say our prior on everything. So prior distribution is equal to e to the minus 1/2. I'll say this is proportional to. Beta transpose beta over something right here. And so this is going to be some variance. So this is my prior variance right here. So what a Bayesian does is they multiply that into that, they recognize everything, and then they go to town. Let's just do that. So work this thing out real quick. Pi beta given x and y is going to be proportional to e to the minus 1/2. And I'm going to multiply these things together, and I'm just going to collect the exponent terms. So this looks like this. Y minus x beta transpose y minus x beta over sigma squared that's the likelihood part of everything. And now I'm just going to add in the prior. So the prior looks like this. 1, I'll say beta transpose beta over psi. And I can compare this thing to this. And they look very similar. So let's just rewrite it the same way. So let's end up letting this be sigma squared over lambda. So if I plug that variance in as sigma squared over lambda, then I get something that's very similar to this formulation. So this is going to be e to the minus 1/2 y minus x beta. I'll write this down kind of like how I wrote it down before. Over sigma squared plus lambda beta in the 2 norm squared. And this is going to be over sigma squared as well. So I'll just extend that. And so maximizing this function, so I'll just say, looking at our map estimator, our map, so the maximum a posteriori estimator, when I maximize this, so I'll just say arg max over beta gives us the map for this, likelihood times prior, maximize it, maximum a posteriori, and the solution to this is the exact same solution that we got here. So I'll just write it down again. X transpose X plus lambda times the identity inverse X transpose Y. And so maximizing this thing is equivalent to minimizing that argument. And so the Bayesian has a slight different interpretation to the problem. They're putting a full distribution on the betas. But in terms of their estimator, it's probably the same as we could write down using optimization and not even think about what error distributions look like. But I like to think about our assumptions in Bayesian ways. So the implied prior, if a Bayesian says that they're doing ridge regression, what they just told you is that their prior distribution is a normal. This is going to be centered at 0, pushing everything towards 0 with this function, and then I've got some variance in here. And I'll just be consistent and say that that variance is sigma squared over lambda. Now, you just pick this to be something. So, I don't know what sigma squared is. I'm going to try to estimate what a good lambda is that gives me a good solution. Now, you have to come up with some criterion as to what is a good solution. So what some people do is they will subset their data. They'll hold a little bit of data out of everything, and they will fit this model. They'll come up with a solution. And then they'll compare how good their predictions are to the true data. So they'll fit their model, and then they'll look at their held out data set, and they'll see how close the y's are to the x betas under this solution. And they'll do that over and over again, and they'll average that difference. That's called cross-validation. And so I would recommend look up what cross-validation is on Wikipedia if you haven't seen it. We can maybe answer some questions on it if they come up at the next lecture, but for right now I'm going to assume you know how to do that. So a lot of times people will just iteratively fit their model and see the discrepancy between the truth and their fitted model. So they'll look at those residuals.
So it seems lambda is the ratio of variance from the data and the prior, right?
It's an interpretation, but yeah.
So why the lambda will turn out to be the ratio of the two distributions?
All I'm doing is I'm showing you the correspondence that this, if I end up just plugging in psi right there, I'm basically saying the same thing as over here. And so I wouldn't interpret it as a ratio like that. It doesn't have a physical interpretation to us. It's just that this is placing a penalty on how much we want these things to be zero. So it's the same influencer as over here. So all I'm doing by writing all this down and giving you this interpretation is to align the two interpretations. So it's not something you do in practice. It's mathematical insight. So somebody might solve this problem. I might choose to solve this problem over here. And while my psi isn't exactly the lambda, there's a correspondence. So there's some psi I could pick to give me exactly the same solution as over here. So that's all my point is. It's not a practical thing. It's just a comparison. Does that make sense, Han?
Yeah, yes.
Cool. So, yeah, I'm just kind of saying when somebody says they do ridge, if a Bayesian said it, what they just told you is they put a normal prior on everything, and the question mark would be, how did you pick psi? And so some people, usually the typical answer would be, I cross-validated. I subsetted my data set, I fit everything on one set of data, so I have my beta hats from that, and then I looked at this set of data, and I fit it to the model using this beta hat, and then I say how close that solution is to the truth. That's a big question mark. What do you mean by how close? And so you get to choose that criterion. A lot of people look at mean squared error or something like that. And that would be the natural choice just because everything is already in the 2 norm. I'm not going to say too much about that right now. We can do a practical discussion of this, I think, next time. Okay, there's another thing that people do. How am I doing on time?
It is 1:12.
1:12. Okay, so I'm just going to say one more thing, and then we're going to wrap it up, and I'm going to come back and I'm going to implement some of this for you, and we'll see how this all works. The nice thing is that a lot of this is already built into software. I remember going to graduate school and there was nothing that was built that actually worked. And so you had to just program it all yourself. But times have changed. So here's a different method. And it's very similar to ridge regression, but it's called a lasso. And so this is called the least absolute shrinkage selection operator. So one way to think about this is where the name actually comes from, is You can imagine how a lasso works if you've ever seen a rodeo or something like that, where they take this rope, they throw it over something, and then they pull it tight, and the lasso will cinch down on things. So the metaphor is coming from that right there, that you cinch something, but what we're doing is we're going to cinch the betas towards 0. This does that as well, but this is working in the 2 norm, the squared error norm. This is going to be operating in the absolute norm. So let me just write it down. So beta hat lasso is equal to the arg minimizer y minus x beta plus a penalty. So this I usually call a regularizer. And both lasso and ridge are regularization techniques because I append a penalty. And in our case, it's going to look like this. Sum of the beta p's, I'm not going to square them, I'm going to take the absolute value. And I'm going to put some penalty on it. And so there's some penalty right here. Now this solution is entirely different from this solution. And one of the main differences in deriving the solution to this right here is that you cannot do calculus on this problem. So why? Because of this absolute value sign. So this has little sharp corners all over it. And so I'll just draw all this for you. But let's just say this is beta 1 and this is beta 2. I'll just draw it in 2-dimensional space. This is 0 right here. So that's just the 0, 0 point. And if I were to draw what this function looks like, it's this little diamond-shaped thing. Let me draw what this looks like, just for comparison. So this right here looks totally different. And most of you will recognize this thing is a circle. This is beta 1 and beta 2. It's the same sort of thing. And so the penalty has a different function form. Depending on what lambda is right here, is it's going to be shrinking this circle. And the effect of this is going to be shrinking this diamond. But what I want you to notice is that there's these sharp little corners at 0 points. And those sharp corners have an influence in the optimization, that it will push some of the betas exactly to 0. And so if you crank up lambda a little bit, it'll start pushing more and more of the betas towards 0. And they'll be absolute zeros. And some people really like that. They don't like stuff like this solution where you only get close to a 0. This will actually provide you zeros because of those sharp corners. If you're an optimization expert, you'll understand it. So if you're operating in a simplex and you're optimizing in this direction, it will optimize at the 0. So I'll say not a lot about that since this isn't a full-blown optimization class. The unfortunate part of this solution, although the fortunate part is you get absolute zeros, is there's no closed form solution. So no closed form solution. And this is a big deal. So I need a computer to come up with the solution to this problem. So in the 1800s, we could solve this because we can write it down. And as long as you can invert this matrix, everything else is easy. If you tried to present this in the 1800s, nobody would be able to solve the problem. And so usually you need an iterative algorithm. So the iterative algorithm I think most people use is called least angle regression. We're not going to go into the details of it, but I'll show you some code next time. And so somebody's already gone through that optimization for us. This has a correspondence to a Bayesian solution. So the Bayesian interpretation is basically the interpretation about the prior. And so we see this part of everything is Bayesian. So I see this as part of the likelihood function that I'm looking at. So this is going to correspond to the prior, just like we had done over in ridge regression. And so the Bayesian interpretation is that you're playing around with a prior distribution that looks like this. E to the minus, I'll say, psi times, I can't write it out as easily as I'd like. I'm going to put this as a product. I goes from 1 to cap p. This is going to be e to the minus psi beta, let's call that little p. Beta p absolute value. I'll say just one or two more things about this and then we'll conclude. And we'll come back next time and I'll show you how we play around with all of this. What does this look like right here? This looks like this. So it's 0. Has a sharp peak right there. This is also not differentiable at the zeros. So this is going to be pi beta p. Or these are the pi beta p's right here. So individually, each one of those betas contributes a function like this, and there's a little sharp corner. We'll look at this distribution next time when we pick up, but it has a name. It's called the double exponential. Why? This looks like an exponential distribution over here. So it's the positive part of this. And this kind of looks like an exponential, but it also lets things go negative. And it has this flipped exponential form over here. So these are both exponential curves, I should say. There's another name for this that I know of. It's also called the Laplace distribution. I included a paper online, and you might want to have a look at it. It's one of my favorite Bayesian papers, and I mean this. So it's probably in my top 10. I really like this paper. This is Casella and Park that put it together. And it shows you how to implement a Gibbs sampler using this prior. So this is hard to sample from because of these corners. And they have a neat little mixture trick. And you can look at the paper on that. But what I want to conclude with is when a Bayesian says they're doing the lasso, or they say I'm doing Bayesian lasso, what they mean is they've got the same likelihood function as before, e to the minus 1/2 this function divided by some variance, and they're multiplying by this prior. So Bayesian lasso means Laplace distribution is your prior. Bayesian ridge means your prior distribution is the normal distribution. And that's what it is. This is a much more computationally intensive thing, but if you're willing to do that computation, you get actual zeros. Now again, the question is going to be, how do I pick this parameter right here? And there's some correspondence between that and this. So it turns out in the Bayesian interpretation, this parameter right here corresponds perfectly to that lambda. We're going to pick up next time. We're going to look at Casella and Park's paper. I'm going to show you some code, a toy example using the lasso, but what I want you to be thinking about on your homework is how all of these different methods compare to each other. If you did lasso, if you did ridge, if you did SSVS, how different would those answers be? And it turns out probably very different. And so saying that, if there's a very strong signature in the data, and you've got a lot of data, we might end up selecting close models. They might be the same. But usually the different methods provide you very different answers. And so that's what I want you to think about in the next couple of days before we come back around to this. So homework problem is do a lot of comparisons. If you've got other model selection techniques, stepwise regression, let's say, everybody as an undergrad seems to have learned that thing, you can do that as well. So I want you to compare several techniques. This one, SSVS, and any of your favorites. If you get extensive with this, I will give you extra credit. So what I'd like you to do is propose something to me, what technique you want to compare. And if it's sophisticated and it's interesting, I'll give you some extra credit. How much? 5% for every technique you come up with. So lots of extra credit, lots of initiative. So I'm going to close out, say goodbye to that camera.